Hey guys, and welcome back to my GIS CE375 class, and I'm gonna do the second video of coordinate systems. In this video we're gonna continue what we did so far. We talked about how do we put coordinates for the earth. So let's go ahead and start. So for coordinate systems, we talked a little bit about different kinds of coordinates. We talked about what's the meaning of a latitude and the longitude and latitude, and this is what we call here global or spherical coordinate systems. In other words, when we have the earth as a sphere or a globe, we now have a way to define any location on the earth by knowing these two angles. And this is also another name for it when you're going to see this in the lab, is what we call here geographic coordinate systems. When we have a projection, meaning that we were able to project this earth or this map into a flat piece of paper, this is what we call here projected coordinate system. We're going to see in the lab how does even ArcGIS do this kind of distinction between the global or the geographic coordinate systems and the projected coordinate systems. And they're again based on how did you project this surface of earth into a flat surface. So usually what happens is that since we have now a flat surface, we can now define the x and y. We have two names for it. We can either call x and y, or another name you probably have remembered from your surveying is northing and easting. So for example here, this point here is 2010, and we can have negative, like you can see here. This point here is negative 20 and negative 10. One thing we have to understand in maps, negative is not that favorable. Yes, you can find negatives, but some map systems like the UTM, which we'll also get to know very soon. What's the meaning of UTM? It's one of the projections that we use a lot, the UTM system, and we're gonna and probably you have tested this in your homework as well. We can have something called a false easting and false northing. In other words, false easting and false northing is the way that we want, instead of having our origin to be in the middle and we have negative values, and negative values is not a good idea, then in other words, we don't want a negative location, right? We want always a positive location. And that's why we have a false positive. We have a value which we call here a false easting and a false northing to make every value in our map to be positive. To remind you, what's map projections? A map projection is transferring this three-dimensional surface as a ball or as an ellipsoid or a spheroid into a surface. The coordinate system is superimposed on the map surface to provide the reference framework by which positions are measured and computed. So once we have this, and this is the meaning of the coordinate system, we superimpose it on the map surface so we can know exactly any location on the map. Where is it exactly? Let's now talk about the first type, which kind of understood, but I'm gonna now wrap it up, which is the geographic coordinate system. So a geographic coordinate system, what happens is that we have the earth and we try to figure out, okay, what is the best ellipsoid that we're gonna use. In other words, we either use a sphere or ellipsoid. Once we do that, we start now defining two angles. So they are angles. The two angles, based on these two angles, we can define two things: a latitude and a longitude. How do we do it? Like we talked in the previous slide, we try to slice the earth into small pancakes. So these are parallel circles. Every circle has a smaller radius from the circle before. The biggest circle, which is the biggest radius, which is the radius of the earth, which we talked about last time, about 6,400 kilometers, is at the equator. And once you start moving either north towards the North Pole or south towards the South Pole, then that means that you have a smaller radius of this kind of circle. We call these circles parallels. So line of latitude, we have it in degrees. How do you mean by the word degree? Let's imagine that we have a line from the center of the Earth, and this line passes, or this center of the Earth passes through the main big circle or the great circle of the equator. And let's put another line that points to the angle that you want. This angle here, it's called the latitude. So when you are at the North Pole, this angle will be 90 degrees. When you're on the South Pole, you have now a negative 90 degrees. And that's the meaning of the word latitude when we have this kind of parallel circles. Again, the only great circle is the equator. When we talked about the great circle, remember the great circle is when we cut the Earth, it has to pass through the center of the Earth. That's the great circle. And the only circle in latitudes that's great circle is the equator, which has the radius of 6,400 kilometer, which is the radius of the Earth. To do longitudes, we do a different approach here. Imagine you have an orange or an apple and you cut it from the top. So you have here, it's like you are cutting different slices. It reminds me of my favorite orange chocolate when they're cut into slices. And you notice here the circles are all the same radius because they have the same radius from the center of the Earth. So every angle now, from which angle? From this circle here. This circle is the one that passes through the city of Greenwich in UK, where the time zone was created. This is the city of Greenwich. They call it the prime meridian, where the GMT or Greenwich Mean Time is 0. And this is how they started looking at the time zones. And every now circle, and this is also another great circle, every circle that just turns, you notice here we have another angle. When you look at the center of the Earth, you either gonna move this way, east or west. And we have different ways now to define the longitudes. Either I use east or west, or I used positive or negative. Again, either I use east or west, positive or negative. Also for the latitudes, I either use north or south, or I use positive or negative. So we have different ways to define the angle, either north or positive, south or negative. Another thing in the latitudes, the value is always, the angle is between 0. You cannot go more than 90 degrees. Why? Because this is 90 degrees. You cannot go more than this 90 degrees from the center of the Earth to the North Pole. For the longitudes, the value you can see here, I can go either this way 180 degrees or this way 180 degrees. So the maximum is plus 180 degrees or east 180 degrees, that's the maximum, or negative 180 degrees, which gives you the same point, or west 180 degrees. Putting the two all together, any point on the Earth now has two angles. Let's imagine this is the center of the Earth. The line from here passes from the center of the Earth to the equator. Give another line to your point, and this angle here will be your latitude. And from the prime meridian to where your line is, this gives you the longitude of your angle. The latitude is given this sign here, phi. The longitude is given the lambda shape. So, some prominent latitude lines, and the famous latitude lines. Number 1, the equator, which is the brown surface over here. Number 2, if you go above or north equator to 23.5 degrees north. And this gives you the better shape of the two angles. Then we have something called the Tropic of the Cancer. The Tropic of the Cancer is also known as when it's summertime, is where the sun is parallel to it, and this is what we call here the Tropic of the Cancer. And that's why you find the Cancer sign, or the Cancer, when probably some of you have a Cancer sign if you're born between June and July. The second one, which is north, also when the sun is now parallel in kind of winter time, when the sun is parallel to this tropic, it's called Tropic of the Capricorn, which is also 23.5 south or negative 23.5. These are three of the main famous types of latitude lines or parallel lines. For longitude lines, probably the prime meridian is the most famous one, the one that passes through Greenwich, UK, and it's at 0 and 180 degrees. So it's a circle, so it's at 0 and 180 degrees. This point here is going to be equal to 0 angles and 0 angles. So this point, I think this point is somewhere in the Atlantic. It has 0 angles. We might probably have a look at it we're going to try to check this out in our exercises class. Where is the point 0, 0? Meaning that you are 0 longitude and 0 latitude. It's somewhere in the equator, and it's somewhere in the prime meridian itself. This is another way. Let's imagine that we took the Earth and we kind of also put it in a kind of a flat map. This is actually not the actual projection used. This is the one that we use a lot, which is the UTM projection. So you notice here, if you look at, this is Greenwich, so that's my prime meridian. So you can see here, we go here from 0 to 180 and 0 to negative 180, or like the way you've written here, east and west. And this point here is the same like this point here. So it's like we roll the Earth around itself. Also, this is your equator, and this is the point we were talking about, 0, 0. I told you it's part in the Atlantic, just north of the African West, the west part. So, and you can see here, the maximum you can get is 90 north or 90 south. Okay, now we want to change between longitude and latitude into distance, miles and kilometers. When I give you an angle, it's hard for you to imagine this as a distance. Well, it was found the following: every 1 degree of longitude, when I'm measuring it at the equator, let's put it back here. When I'm measuring 1 degree at the equator, this is around 111 kilometers. Also, when you measure 1 degree of latitude here around the equator, it's going to be also the same 110 kilometers. The problem now is that when you go to the North Pole, this 110 starts to get smaller because all your meridians or all your longitude lines converge here, up there at the North Pole. So it goes less from 110 kilometers to here. So the first thing, if you have a distance on your longitude or between two longitudes and you want to know what's that distance, here is the equation. It's equal, 1 degree of longitude is equal to 110 cosine the latitude. So let's imagine what I mean here. So if I am at the Earth and I am the latitude of 60 degrees and 90 degrees and negative 90 degrees, we want this one and this one. Let's start here first with the 60 degrees. So this is 60 degrees, north to south, doesn't matter. And I want to measure this is the first meridian, and that's the second meridian, and I want to know what is the distance. If the angle here between both of them, these two, is 1 degrees. What will be the distance here? You know the distance here is 110, but what about here? What about here? So for 60 degrees, 1 degree of longitude is equal 111 kilometers times cosine 60. And it's going to give you a value that's much less than 100. 1 degree of longitude at, let's put here at 60 degrees, and let's put here at 90 degrees or negative 90 degrees. It's going to be equal 110 times cosine 90 degrees or negative 90 degrees. This will give you a 0, so the distance here in this case will be equal to 0. The exact values for this, let's read it together. 1 degree of longitude is about 111.3 at the equator, 0 like we did at the pole. For latitude, it's between 110 at the equator, and it gets a little bit more, 111.7 at the poles. So approximately it's again 111 kilometers. Then comes now the more complicated question of if we have now a distance of any 2 points on the Earth with a value of longitude lambda 1, phi 1, lambda 2, and phi 2. Then we have different ways, different techniques to calculate the distance. Please note something, guys. This distance here will be the shortest distance. What do you mean by the shortest distance on the Earth? It's the distance that passes throughout a great circle. And we talked about this when I was wondering why the aeroplane goes to a specific route when it wants to go to Europe, because it's going through the shortest path, which is on this great circle. To calculate it, I put here actually 3 different ways. This is the first way. They are approximate ways to calculate the distance d. Here we try to get a value called a value from c, and this is the best way when we're using Excel. So this is the equation. This is phi 1. Delta phi is the difference between the 2 phi's. Delta lambda is the difference between the 2 lambdas. So here, sine square this value times cosine this value times cosine this value, and so on. And then comes value of c to a tan 2. What's a tan 2? I brought you the value of tan 2 and the definition of tan 2 in your Excel sheet. So if you have 2 points, lambda 1, phi 1, and lambda 2, phi 2, then the distance between the 2 points is, we're going to use something, this is called the Haversine formula to calculate the great circle distance between the 2 points. That is, what's that? The shortest distance over the Earth's surface given as the crow flies distance between the points, ignoring any hills they fly over, of course. So it's like, if I have any 2 points on the Earth, I can go this way, and I can go that way, but the shortest distance is like what we call here a great circle on the Earth. I'm going to show you an example in class using the globe. Another way, if you don't want to use this way, if you don't have Excel and want to use your hand, then probably one of these ways to do it. The distance is square root of something called dx, which here you calculated, and then dy. So it's square root of these values here. This is another way. It's like actually this, square root of dx squared, square root of dy squared. And that's the distance of any Cartesian, but I'm going to do it now with longitude and latitude. So they calculated the difference in x and y. It's like some kind of another projection. We find the dx, the dy, and that's the distance d. So dx and dy, and it's a function you can see here between the longitudes and latitudes. You can use this as another empirical value. Equation number 3, also if you want to have it in just one simple equation, it's 2r arc sine, and you have here the square root of all this value, which is a relationship in lambdas, phi's, and phi's. So we're gonna do some examples finding the shortest distance in class with this kind of form. When we are measuring now the same thing in Cartesian, this is very similar to this equation I put here. When I have, and we probably learned this in surveying, when I have a distance in a Cartesian, what do you mean by Cartesian? Easting and northing. So this is E1 and 1, E2 and 2. So in this case, the shortest distance is just delta E square plus delta N square, which is the difference between the deltas and N's. You probably have done this when you did the traverse, and find the square root, and this will give you the distance between any 2 points in a projected sense. So given all this, now let's define the meaning of horizontal datums. You notice that on the last video and also to this video, we have talked about, okay, once we have now the Earth, and we want now to define what is the best shape of the Earth, so we can start defining these longitudes and latitudes on some kind of a more regular surface instead of this irregular shape of the rock, which is the third rock from the sun, which is our Earth. So we do something called horizontal datums, and the horizontal datums, let's put it in another really easy name, an ellipsoid. We want to find what kind of ellipsoid that will best represent our mapping needs. So it's how to get this ellipsoid. We do the following: collection of points on the Earth that have been identified according to their precise north and south location. So this is my Earth. I'm gonna get a bunch of points where I know exactly where are their locations, and based on these points, we call them, you remember this, benchmarks. We call them control points. If you remember from your surveying, it's something similar to this shape here. It's a brass thing. Once we get this point, there is a computer model that will try to put these points on the best shaped ellipsoid that best represents the Earth. So we know the longitude and latitude for the location. So we are very well surveyed points on the Earth with which horizontal and vertical position have been actually determined. And then we now try to specify the reference frame, which is a spherical and 3D Cartesian. So here we try to find exactly the location of these points, and from that we want to figure out, okay, what is the best representation for that? Through astronomical observations and satellite-based position, we use this type of calculations to find the exact locations, and all other coordinate locations featured in the GIS are measured with reference to these points. So these are my datums. These are points that create my reference points, and we give it also the name datums. So what's a datum? A datum is a reference surface plus a network of precise points. It provides frame including origin or starting point and x, y, z axis. So a reference surface or a datum is a network of these, again, precise points. They provide now a reference. Once I know these points, imagine that you brought some points and you want to model these points. They will provide exactly where is the origin point of a reference surface that best represent these points. It's like some kind of regression analysis, and this will be my reference surface, which is going to be, in this case, an ellipsoid. Once you have the ellipsoid, you can now have some kind of reference towards everything on the Earth. In US, we define something called the NGS, National Geodetic Survey. This is the main body that does all these control points. They put, you can see here, if you look here, you're gonna find here the NGS. So it's and also it's very well maintained piece of brass that they put on the ground with exact location, and you can go ahead and find online where are these network of points. So the NGS datum, that's the one we use in USA. Again, there are points here, like you can see, point D, F, and G. And once you have these points now, you can now relate A, B, D, F, G here. you can now relate your points using your own surveying equipment, and you can get a network of points and a network of lines that will help you survey anything on the Earth. So it's called the National Geodetic Survey. Establishes geodetic location, the latitude and longitude for known points. So here it creates these known points. I know exactly what is the delta and phi for each of these points based on a specific ellipsoid. Based on that, you can now relate to each of these black points here and get your own work, and you start relating to these very well specific points. Sometimes we use these points to start from, and F and G here, or D, F and G are used to check and correct your errors. And we use what we call here, if you remember from surveying, something called triangulation. And if you remember the triangulation, do you remember the sine rule and the cosine rule to calculate any parts of your triangle? So if I know the angles, I can know distances for any of the triangle. So exactly from this point, I can know exactly all the coordinates of every single point in our survey. So again, I know I took you back to surveying, but this is a main basic part of our work in defining your points that come from your reference network. Improved surveying, different estimates of the datum, which we know here the benchmark. And these are some pictures showing you older triangulation networks throughout different parts, throughout Europe, throughout Sweden, throughout different points around the world. And just to remind you, this is the sine rule to do the coordination. I won't go directly through this. We did a lot of this in surveying, I guess, with Dr. Leftwich. So this is the equation that we use to do triangulation in GIS and in surveying. And then we do some kind of adjustment. And if you remember, we had point A, B, we started from our baseline here, and then we started triangulation, and we now were able to fix point here by knowing this is also another point, so we can fix the arrows, so we can fix this point again. This is again what they do again when they do a date adjustment for the datum. The more points they survey very well, the better datum they can get. They can now also start fixing A, B, D, G, and E. So coordinate locations are estimated for both old and new datum points, and then they kind of adjust their datum. And that's why in ArcGIS you find different versions of datum, different versions of ellipsoids. Let me give you an example. We have here two ellipsoids. The first one is this one here, and the second one is the one with the origin here. So this is ellipsoid A, and this is ellipsoid B. Ellipsoid A is the first one. Let's say it's the one from 1866. Remember that? How did they get it? Using just one point here and one point here. 2 points, and they were able to fit this surface of ellipsoid around these two control points, or these two benchmarks, or these two datum points. And then, because we had more techniques, we were able to add now point 1, point 2, point 3, point 7, 5, 6, and all these points. Given these different points of surface, we were able now to adjust ellipsoid A to become ellipsoid B. Since we have different ellipsoids, the point moved, the origin point moved from here to there. The semi-major and semi-minor axis or radius change from here to there, so we can have some kind of adjustment. So when we add new points and surveying improvements, data updates, and we re-estimate new coordinates of datum points, including the estimate and position of each of these points. And once you do the surveying year, they will be related, let's say, to point 5, 6, and 4, and they will also be updated not on this ellipsoid but on the new ellipsoid, which is the new reference. Which one is the best? I don't know. Nobody knows, because the ellipsoid, this is my Earth. Each ellipsoid tries to best represent the Earth. There is no better solution. this might be the best, this might be the best. They have different ways. This might be the best to map this area, this might be the best to map this area, so we can have different ellipsoids. Each one should be the best to map specific area. So the most famous two datums that we're going to be using and you're going to see a lot in ArcGIS, this guy here, NAD27 and NAD83. The first one it was done in 1927, the first datum points, and it was based on this, remember this, 1866 ellipsoid, and it used 26,000 points throughout the world to create, this is NAD27, the red one here. I'm not going to put my red marks just to show. See how doesn't it represent the Earth well? But it might represent the US or the North American part really well. And then in 1986, they started a new reference point with more points, and they used instead the GRS 80 ellipsoid. Now see how many points extra? From here to here. So it's a huge shift. You can see now the huge shift from this red ellipsoid to the see how the blue one now tries better to represent the shape of the Earth. They both look egg-shaped, but this one is a little bit better than the one. So here you're gonna see also this GRS 80. Another what we talked about that's being used a lot, especially by NASA and by GPS, is another ellipsoid, DWS 84. So the data that you're gonna get in your ArcGIS work will be either using one of these different ellipsoids and one of these different coordinate systems, or what we call here reference points. This is the network of datum points just in the USA and Canada and Mexico. You can see here how extensive it is. Some points are even in the ocean, or not the ocean, it's on the ocean bed. So you can see here these points create what we call here a horizontal datums. So NAD83, from NAD83, they didn't stop in 1983. Different other datums came by up till 2011. I think there's a new datum that's coming up into 2020. It doesn't matter, we're trying to map as accurate as possible, and these are ways to put more points and find the better reference surfaces. So we have something called HARN, something called course network. Here we use GPS data. NAD83, but not the original. It goes course 93, so it's like an update in 1993, or NAD83 that was updated 2011. So these are different, you can say, orientations from NAD83 datums. The WGS 1984 we talked about, also it was updated in 1987, and then we have this one here, WGS 84 ellipsoid, which is very similar to the GRS like I showed you in the previous slide. There is something called ITRF, International Terrestrial Reference Frame, and we have different versions of this ellipsoid. Which one is the best? Well, let's see here. If you have a point, and this might be a little bit weird, if you have a point, this point here, this is one of the reference points in NAD27. If you map it using NAD83, it will be here. And different versions, you can see now the difference, and this is the different longitudes and latitudes. You can see the shift went from almost 40 meters to centimeters now. And then came another big change between the NAD83 to the WS, the one we use again by our GPS. So this is the change between the NAD and the WGS. So you can see here, the point went from here, it moved to here, the same point, we're talking about the same point. And they're all here now for you. So you can see now the difference from here to here. You can see it's in matter of centimeters. And then came this guy here, which is the WGS 84. These are the same point, but it's being plotted in different coordinate systems. And that's why when you map using different coordinate systems, you might find some problems with your data. You might find a city here and another city over it. And if you remember in our last lab, that University of Charleston was on the other side of the river in Charleston, which was wrong. So it moved it away to the other side of the river as a problem with your data. We're going to fix this in our next lab. let's now talk about vertical reference. I'm just going to go ahead and introduce it, and then I'll let it to the next video. Vertical reference is also similar to horizontal reference, but now we're talking vertical. Again, the Earth looks like a very irregular shape, and we want to know also not only to map the location, we want to map also the elevation. So, if you remember from surveying, you had something called contour maps. Contours that shows you the mountains and valleys, and each line had a number. Or when you had a mountain, you said this elevation here is a number 200. What was this 200? It refers to what we call here elevations. Elevations refer to what, or what was my base. Usually when we have a project, we start from 0 and then we do our elevations. But when we want to relate it to the Earth, we relate it to this guy here. MSL stands for mean sea level. So how do we measure mean sea level? Well, we used to measure that early time. They used to measure the sea level in 110 days, and they found the average based on ebb and tides of the ocean, and they said this is the mean sea level, and then they relate everything to the mean sea level. Why did they use the mean sea level? Because of what we will learn today, something called the geoid. That they found that's the best way to define difference in elevation. So the word geoid is a imaginary surface. It's not a surface that you can see. However, you can feel it using specific equipment. It's an equipotential surface. So it's a surface with something equal there. What's the equal? The potential. What's the meaning with potential? Of the Earth's gravity field that best fits the global mean sea level. Well, you know that water in Earth is there because the gravity pulls it away. The only thing that pulls it up and down is the moon, which gives you the ebb and tide. So the gravity of the Earth is best holds the sea surface and ocean surfaces to its core, and based on the gravity here we can create a surface. So let's imagine that we don't have land, all oceans. So it's the shape of the Earth. If all oceans allowed to fall freely to create a single one surface that's only affected by the gravity of the Earth. So will it give you an exact shape of a sphere? Actually no, because gravity is not the same. You can see it, this is a color-coded shape of the Earth showing the gravity power in different parts of the world. So it creates as a single undisturbed global sea level covering the planet. Let's imagine that. So this would be what we call here the geoid. Since we don't have it, we use it using the gravity. So this is what we use now. What we did before is horizontal reference. This is called a vertical reference. What is the reference point? And now here the reference surface where I can measure elevations of several points out the Earth. So the geoid, let's give it a definition now. It's a three-dimensional surface. It's surface, it's not a sphere, it's not an ellipsoid, it's just a surface, along which the pull of gravity is constant, meaning that here, if I was able to measure how much the gravity will pull me here and here, the pull of gravity will be the same towards the center of the Earth. So gravity is not constant, or it actually changes from space and time. It is a reference against which heights are measured and measured an interpolated surface. So here it's an interpolated surface. Theoretically, it extends at mean sea level. So let's imagine that we have here, this is the sea, and this is a mountain and some land. Let's imagine that the sea continues throughout the Earth. Seas and oceans, this is called the geoid. Theoretically, it extends at mean sea level. It's a little bit different now than mean sea level, because now it's not based on like we did before on the actual sea level. Now we use different observations from satellite, and also we use some gravity measuring instruments, and it's based on some observations. We don't use, because since oceans has currents and wind and hurricanes, it's not the best way to do that. and also the moon pulls it away using the ebb and tides, so it's hard to do it as mean sea level. So now we use instead the geoid. So this is one shape of the geoid based on the gravity. You can see here the gravity. This is the least gravity possible, and this is the highest gravity possible. Notice something? When we have some kind of mountains, for example the Himalayas and the Everest and the Rockies and the mountains in South America, I'm going to ask what's the name of these mountains. You're going to notice that the gravity is at its max. At the ocean, especially here, the gravity is the lowest, and this gives you the shape of the geoid. It's based on something called the NASA Gravity Recovery and Climate Experiment. It's a project done by NASA, a satellite that was able to calculate the gravity values and the gravity formation summarized. They summarized over a few days because it changes from day to another. You can notice here it's greater over continents, less at oceans. When we have a thick crust, you have more gravity, and that's exactly what Newton tells us. When we have a body, then we have more gravity, and that's what happens when you have a thick crust at the mountains. Okay, remember the geoid A and geoid B? I just need to move the slide to a previous location here. And I'm gonna stop here, guys. I'm gonna do the third video about geoids. I'm gonna talk more about geoids next week, so the third video will be more related to next week. And we have let me just, before I end, let's start here. In early times you used to plumb bops to find the location, the location where the gravity takes us, and we use something called gravimeters to calculate the geoid. And again, the GRACE project, the one done by NASA or GOC satellite, the distance between satellite orbit planes changes due to gravity. So they use, satellites don't have power, they just go there with gravity. So the distance, if it goes up and down, we can measure the distance of this satellite. So again, we have here the Earth. When the satellite is here, it might have more gravity than here. So it was able, once it starts going throughout the Earth, it will measure the gravity using this kind of satellite. So we done some statistics, and based on that they were able to create here the geoid. So we're going to talk in the next video about what's the meaning of the geoidal height and how to calculate the geoidal height, which is here. I'm going to leave it to the next video, and we're going to also talk about vertical datums, and then also next week we're going to talk more about how we do map projections. So by this I end this video, and see you guys in the next video, and have a great